let's move on and look at how we can use the LIBOR market model to get something more theoretically pleasing for a closed form formula for swaption prices. Earlier we have looked at that if we were to assume the swap rate follows a log normal process, we are able to derive a closed form formula for swaption. But then, it depends on the swap rate being log normal, which is a little restrictive, right? And here we have a much more flexible interest rate term structure model. Then how do we utilize that additional flexibility here and yet obtain something that is, from a computational perspective or analytical perspective, something simpler, where basically to get the best of both worlds, where we can have a closed form formula, but yet we are able to inject more richness into that closed form formulation. Now let's see how we can start that. Well, basically to recall that if the swap rate would follow a log normal process, we basically are able to price our swaption like this, right? This is Black's formula. And it is very good because it's a closed form formula, right? But we want something better. So what do we do? Now, in order to have this closed form formula, we require this volatility term here being as constant times this swap rate here. But if we relax that a little bit and not having a constant, but having a function of time, we can still calculate a constant parameter in the sense where if we can calculate a square root of this integral here. So if we have b is a function of time, so as it goes through time, has different values, but we can get an average. And if we plug in the average there into this formula, we can still have a closed form formula to calculate a swaption, whereas we do not restrict this being a constant over time. So then to be able to do that, we have to calculate this b squared here. And we can do that by having this thing using something similar or using something consistent to the LIBOR market model to get the b square, and then to use this process to get this sigma here. So let's see how we can do that. Well, it's probably worth some review. So take a look at example 3.5 before in lecture 3 about the using the annuity as numeraire. So and how things have been derived and so on, right? So basically take a look at that. Now, in order to calculate, to utilize the closed form formula and with some flexibility injected by the LIBOR market model, we'll see that we basically need connection between the swap rate and the forward rate that we generated from the BGM model. So what's the connection? Well, the connection is that the swap rate is this thing here divided by the annuity factor, right? So your current time t, this is starting point of the swap, this is the finishing point of the swap, and you have this NTUT factor defined this way here. Now, the relation between zero coupon bond price and the forward rate is this, right? So the next period, TI to current time T divided by T starting point of the swap, T naught to T will give you this, is equal to the product of this thing here. So it's basically the little ones from T1, T naught all the way to Ti plus 1, Ti minus 1. So if I is 5, will be from 0 to 4. Okay, and then product of this one. So the little chunks in between, you have to multiply them through. So now this gives us a, first of all, a process between a relation between the forward rate and the zero coupon bond prices for the ratio of that. And also from the zero coupon bond prices, there's a relation between the swap rate and the zero coupon bond prices. Then between those two, we're linking the swap rate to the forward rate here in the LIBOR market model. Now, I'm gonna present the result first. I'm gonna derive this result. So basically, the B square we needed for the formula earlier here to get this sigma that we can use here is really the is this expression here, somewhat complicated expression. And so, but we'll show that why this expression, so we have this B square having this particular expression. So how do we do that? Well, and we do this by exploring this condition that we have seen earlier. And here, basically, the B square is linked to the volatility of the forward rate. This is beta term is really the beta K. Q is really Q's component of volatility of this FK here. Now, if we start with this, so this swap rate is this thing here, right? And basically the denominator is this annuity factor here. And we also know that big TI is equal to this one, PT T naught, which is the starting point of the swap, and multiply by all the ones in between, right? So this whole bunch of forward rates. So if it's to TI, then it has from J to 0 to I minus 1. Now, we have those two conditions. And now from here, we then say, let's have an expression for Tn, P little t, big Tn. And let's also have an expression for the denominator, each of those P, T, Ti plus 1. So this T, little t, Tn from here is this, T, PT, big T naught times all the way from I equal to 0 to n minus 1, because we need a Tn here. And this Ti plus 1 is this PT, P little t, T naught times this product with the index on I, J equal to 0 to I, because we have I plus 1, so it's I here. And here's n, is n minus 1. Okay, so we have those two expressions. Let's substitute those two expressions into this for this and for this. So we put them in, we find out that we can cancel the one here. There's a common factor here from this one here that we can pull out, and we can cancel that. Then this ST becomes this expression here. Okay. Now there's this thing here, 1 divided by 1 plus tau j fj, and there's also 1 here, but it's within the product index here. So there's something we can cancel there as well. So let's divide the common factor here, which is from 0 to n minus 1. So once we have divided this st, the swap rate will become this. Now, once we get to this point here, essentially we have found a link between the overall swap rate at a particular time t and all the forward rates observed at that little t. Okay, so there's a relation here between the swap rate and the forward rates. And then we can explore that to determine the B factor that we're looking at. So we see that if we have a swap rate, the swap rate process will have some drift and have a B as dz here, okay? So this is really the B we're looking for. B specifically is B square we're looking for that we can use to substitute. Because this is the volatility part for the swap rate. Now we have to determine this from this process. So the process for the forward rates, each point on the forward rate curve is some form here. Okay, so we're using the multi-factor process just to be generic. You can also do a single factor here, but to remind you that the swap rate here is a single factor process. Okay, so we basically this is like a summarized information of all the information that we have, the more flexible structure that we have here. So by Ito's lemma, we look at this. What is this part here? Well, if your swap rate is this, then its process, the volatility component of that process, must have this partial derivative here, right, times this, if S is a function of this Fk's, which is given a specific form here. Because for each of them, then we have a partial derivative that we need to multiply through. Okay, now we have, so we're basically doing it for each of the Q here. For each of the Q, there's a sum here. And the sum comes from here that we need to have a partial derivative. So you can, if you look at it, if B times S is equal to this, then B itself is this thing divided by S, right? So you can, S is a function of T, so for a particular T, this S is just a number. So you can just carry that all the way inside all the indices here. So you put it in the innermost index. Now, so this divided by ST is this BT here, right? So what is the green one here? Well, now if you actually take the partial derivative here with this expression with respect to Fk for each of the k and divided by St, and you will actually find what's here is this term here. Okay, now, and if you have that, so your BT now is equal to this expression. So this green one is being replaced by this, and the yellow one is still the yellow one. So this beta here is this thing here. I just rewrite it in a different one just to be consistent for notations. So it defined this beta KQ as this thing here. Okay, so you can write as beta. Now, so your BT now is expressed in everything you have available from the BGM model. So if you simulate the BGM for each time period, little t, then you'll get this BT here from here. Now, although we know the BT, what we really need is the B squared T, right? So we have to have the square term here. So the square here will involve the cross factor as well. But since the random factors, they are independent random factors, so the cross factors dropped out. Okay. So with the cross terms dropped out, so your B square, you would just have this relatively simple expression here. Okay. So, okay, let's see. Then once you have this, you can substitute it back. So you have the B square is for each of the time there. So basically B as each of the simulated time you have, you get a B square. And that's where the B square tau here. So you have a whole bunch of numbers for each of the time. So you're basically integrating that from this time 0 to this time t tau, which is the starting point of the swap. So if you have a evolution from a simulation, you actually have discrete time periods. So here you will not have an integral. Instead, you will have a sum. So sum, you'll add up all the B squares for each of the time period. Okay, and then you add them up, and you calculate the average just divided by the entire period of time. Then, so this part here depends on your time steps, and here it depends on the, divided by the total time. Then take a square root, you get your sigma here. And you can plug in that sigma for to calculate your swaption. So this basically allows us to utilize the flexibility of the LIBOR market model, yet we end up still with a closed form solution that allows us to calculate swaption prices relatively easier. And recall that in the last lecture, we talked about calculating swaption prices where we have to use a single factor short rate model. And we go through some tricks and to allow us to calculate swaption prices. But here is another, in a way, it's another trick. But we essentially link the flexibility in the LIBOR market model, which is BGM, and that one can be a multi-factor. So we actually have a multi-factor model here. We just utilize the flexibility of multi-factor model and to get our swaption prices. So that we have more richness in the model itself. Now, why can we really do this in the valuation to get this sigma here? Well, in the standard model, we basically assume that sigma is a constant, but we don't have to make that restrictive that assumption to be. We don't have to assume it to be literally a constant. So we don't have to be that restrictive. Instead, what we really need is this being an average. So as long as this is an average, the standard model will work. So this is what we're exploring here. So we relax that a little bit. And so we have a B being a function of time. But as long as we calculate the average, we then come back and use the standard model to calculate swaption prices. All right. So that's basically concludes the HJM model and the BGM models.